In this video, we're going to take a look at something called significant figures. And that relates to measurement because in science and chemistry, we take a lot of measurements. So whether that be measuring the volume of the graduated cylinder or measuring the mass of something with a balance, uh, in our measurements, there will be what's called uncertainty. It's not going to be exact. There will be some error most likely due to our measurement methods, our tools, errors, so on and so forth. So when we talk about measurement, there's a few terms you need to know before we go into how this relates to numbers. There's a term called accuracy and a term called precision. And so accuracy is how closely your measured value will agree with the correct value. So we can look at the picture over here. Let's say that the correct value is in that red spot there. That's the correct value. That's known based on experiments, based on actual measurement done by other scientists. Um, if you're very close, if your measurement that you did in the lab is very close to that spot there, to that red circle there, that means your measurement is quite accurate because you're close to that red spot. And notice these are, for example, other measurements that you took, but you were a little bit off from the red circle. But the point is that you're not too far off. You're not all the way in the blue. You're not, way out here outside the blue. You're close to the red. So your measurements are accurate, but you wouldn't call these measurements here as a group precise. Precision or precise means how closely your individual measurements agree with each other. So when you do a lab, you might mass something a few times, you might measure volumes a few times, you might do a few different trials. And so you'll notice over here that let's say all these X's on this picture here are all different trials. They're all pretty close together. So maybe you had 23.1, 23.2, 23.3, 23.4, 23.5. These measurements would be considered precise because they're all very, very close to each other. But they would not be necessarily be considered accurate because you did some research and found that the actual number was probably around this area here. So it was probably, let's say, I don't know, 15 instead. So your measurements themselves, they're considered precise because they're all very close to each other, but they're far from the actual truth, the actual number that's actually reported. Um, Whereas in this picture over here, you can see that we have a bunch of measurements taken. They're all close to each other. A little bit, they vary a little bit, but not too much. And they're also right on the red circle, so they're very, very close to the actual value that you want to research later on. And so these measurements here would be accurate and precise. So let's talk about exact numbers versus measured numbers. So in science, when you take measurements, you will always have some degree of uncertainty. There'll always be some degree of error there. Now, there are some numbers called exact numbers where um, you you know for sure what the number is, and there will be no uncertainty in that. So there's no uncertainty in an exact number. So for example, if I were to come into a room and there's three people there, I can say there's one, two, three people. There's no uncertainty. That's an exact number. Or if I open a carton of eggs, there's one, two, three eggs in there right now. That's an exact number. There's no uncertainty there. But whenever you actually measure something, so let's say, for example, you're measuring, like I said, something on a balance or something on a graduated cylinder, or even something with a ruler, you're going to have some uncertainty there. You're going to have some uncertainty. And so you need to somehow communicate the fact that your number is not exact. You need to communicate the fact that there's some error that's going to be there because there's limitations to the tool that you use. So, to communicate our uncertainty in our measurements, we use what's called significant digits. We might also call these significant figures. Figures. And I might say sig figs, for example, just to shorten it. So, when we talk about significant digits, when you're measuring something, like I said, there's measurement error, there's uncertainty. When you're measuring, you record your numbers that you're measuring, but then you also have one more digit that you include, which is where your error is likely going to be. So that last digit is that digit of uncertainty. So, for example, let's say I was looking at this ruler over here. Here we have, if I measure, this is 0, 1, 2. I'm pretty certain, so up until this point here, 2, I'm very certain. But then once I get to this point over here, um, It could be 2.2, could be 2.3. So there's some lack of certainty in that last digit. So if I write 2.3, scientists will understand that I mean that it could be 2.2, maybe 2.3. There's some error there. I'm a little bit off. So this last digit here is where the uncertainty is. Now let's say I get a ruler that's a little bit more precise, with more divisions. So notice over here, I'm certain about my 2. Then I have 1, 2, 3 lines there, and I'm just above the third line there. Okay, just above the third line. So I'm certain in my 2 for sure. I'm certain in my 3 here, but I'm not certain in my 5 there. So I say it's 2.35. I'm halfway between the 0.3 and the 0.4 line, but it might not be 2.35. It might be 2.34. It might be 2.33. It might be 2.36. So in that last digit, that's where my uncertainty is. That's where I have some uncertainty. Because here I'm measuring, so I don't have exact numbers. And so you'll notice we have some examples here for measuring volume in a science lab. Volume. If you measure with a beaker, for example, a beaker, there's not a lot of divisions. There's not a lot of divisions there. So for example, I have 20, 30, 40, 50, 60. Here, I might say, so let me erase that to take a look. I might say the volume, I'm not too sure. I know, for example, that I'm above 40, but below 50. So I might say it's about 49 milliliters. I might say that. And so I have uncertainty in this one here. Is it 48? Is it 47? There's uncertainty there, so there's a greater uncertainty. It's not very precise. But then I can get a tool that's a bit more precise. I can get a graduated cylinder, and I can measure volume that way because there's more markings there. So you'll notice that I have 35 at this line here, 40 here. So this is 36, 37, 38, 39, 40 here. Okay. So I'm past the 36 mark. I'm a little bit above the 36 mark. When you measure the water, remember you have to measure from that meniscus, this little curve there. So it looks like I'm probably about, I know I'm 36, and then maybe in between 36 and 37, so 36.5 milliliters. And this is where my uncertainty is now. I'm more precise though. My uncertainty is in the this 10th place over here. And I can get even more precise than that. Here's another tool that you'll learn about later on this year. This is called a Buret. And so when you measure the volume of the Buret, you kind of measure going this way, so 20 to 21 over here. And so I'm going to, well, I'm going to measure the other way for now just to show you what I mean so I don't confuse things. So here I have 21 and here I have 20. Actually, let's go to 20. Let's keep the numbers going up actually. So 20 and then over here all the way down to 21 here. So that means all these markings here are, if we look carefully, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then finally this is an extra one. So these are zero point 0.1 increments here, 0.1 increments. So let's say I want to measure that in 0.1 increments over here. You'll notice it's a lot more precise for my volume here. So I have 20, and I have this 20.1, 20.2, 20.3, 20.4. So I'm somewhere in between 20.3 and 20.4. So it looks like I'm even a little bit above the 20.45 mark. I'm more than halfway there. So I might say this is 20.4, let's say 8 milliliters. So my uncertainties here are more and more precise with the more divisions that I have. I still have uncertainty there. It's just that now it's in my 100th place as opposed to my 10th place, a more precise instrument. But the point is that you do need to record these significant figures properly to indicate that you have uncertainty. Scientists will know that in your numbers, when you reported them, that there's uncertainty in certain digits. And you need to know how many decimal places to report to when you're using tools like this. If you were to look at this and say, at this beaker and say it's 49.56784, you're lying and saying that you can see so many more divisions than are actually there. So it's kind of based on the number of divisions that you can see. So basically, why are those significant figures important? Well, to really answer that question, I want you to watch this video here. It's a great video that goes over why you need to take them into consideration. But the idea is that you can't lie about how certain you are about your measurements. Otherwise, you're throwing people off with your studies. Let's go take a look at some examples of how to identify significant figures and also how to take into consideration significant figures when you're doing calculations. So these are the significant figure rules over here. There's some video tutorials that you can go over and also some optional videos for more practice. So these are general rules that you need to follow. All digits from 1 to 9 are considered significant figures. So for example, if you have 129, that is 3 significant figures in that example. If you have zeros in between digits that are significant, so for example, here we have 2008. 2 and 8 are significant, the zeros are in between. So that means that there's 4 significant figures there, the 2, 0, 0, and 8, because the zeros are sandwiched in between 2 significant figures. Then you might have what's called trailing zeros. So trailing zeros, for example, we can see here we have 2000. 2000. Those are zeros that come after a significant figure, for example. So if you have 2000, these zeros here are trailing zeros. And so these are not considered significant. They're still there, but they're not considered significant. And so this here is my significant digit. I only have one significant digit in that case, one significant digit. If you have trailing zeros with a decimal place, then you basically made everything before it and after it significant. So for example, here I have 2000.0. So this is 5 significant digits now because I put that 0.0. Over here in the 2000, I didn't have 0.0, but over here I have 200.0, and I've made everything here significant by doing that. So here I have 5 significant digits. You could have also done this if you want to only have 4 significant digits. You could do this. You could do 2000 point, and that indicates that you have 4 significant digits instead. Leading zeros are not considered significant. So for example, here I have 0.0035. These zeros in the front here, because they're not sandwiched in between anything significant, they're not considered significant. So only the 3, 5 are considered significant digits. So this here has 2 significant figures. And if you do scientific notation, all numbers are considered significant in scientific notation. So over here we have 1.344. That means there's 4 significant digits. Don't count the 10 and the exponent. Just count the decimal before that term. And exact numbers, you can think of them as having an infinite number of significant figures. So we almost don't really consider them when we're doing our work that you'll see later on. But for example, if I say there are 2 people here, since this is an exact number, they have it's an infinite amount of significant figures there because you're counting 2 people as opposed to measuring. They're not measured numbers. So it's really when you have the measured numbers that you have to take into consideration these significant figures. So you should be able to do some examples to identify how many significant figures you have in a term or in a constant. So for example, if I look here, these are all digits from 1 to 9. There's 3 of them. This would have 3 significant figures. Over here, I have leading zeros here, so these do not count. But these 2 are significant figures. There's 2 significant figures there. Normally the 0 wouldn't count if it was something like this, 50, okay? But in this case, because I have a decimal place there, if you have zeros with your after a decimal place like that, then they do count. So if I had written, for example, 0.005, that there's 1 significant figure, and then once I put this, that's 2 significant figures total. I didn't have to put that if I didn't want to put it. So it's really 0.005 is one significant figure, and this is two significant figures. Over here we have 30. Normally that would be one significant figure, but we put our decimal place and we added zeros after. So each of these are all significant now. So we have 1, 2, 3, 4 significant figures. Here we have 230. There's no decimals, so really it's only our first two numbers are significant. So we have two significant digits there. This is a bit ambiguous here. What I mean by that is, when we report a number this large, do we actually mean that there's only one significant figure? Because there's no decimal. So we have, whoops, not 9. We have one significant figure, and it's the number 9 there. If I really did want to express that this was really only one significant figure, to make it less confusing and ambiguous, I would have probably reported that in scientific notation. If you don't remember scientific notation, please make sure you review it in the review video. And then finally here we have scientific notation over here. Remember, all digits in scientific notation are significant. So we have 1, 2, 3, 4, 5 significant digits over here. So the purpose of identifying all those significant digits in your measurements is because when you do calculations, you need to follow what's called significant figure rules. And so there's different rules for whether you're doing addition, subtraction, and multiplication, division. If you're doing addition or subtraction, you need to count the decimals. Your final answer needs to have the same number of decimals as the measurement with the fewest number of decimals. So for example, if I look here, I have 2.5 and 3.72. And so if I do that in my calculator, I get 2.5 plus 3.72, I get 6.22. If I keep it like that, that's a bit of a problem, because notice that for this over here, I only have one decimal place, and my final answer somehow is more precise than my less precise measurement. Okay, I can't have a final answer that's more precise with more decimal places than my measurement that's not very precise. Okay, otherwise I'm kind of lying about how good my measurements were and how good my tools were. So I really need to round this to having only one decimal place. And so if I have 6.22, I want to round it so I only have this number here. If I look next door, it's a 2, so I round down to 6.2. So let's try this example out here. So we have 34.89 and 21.1, and then 39.88. And we need to add these up and then round to the correct number of significant figures. And so if you look carefully, this number here has the fewest decimal places. So we're going to have at the end an answer that has only one decimal place. So we're going to plug this into our calculator, 34.89 plus 21.1 plus 39.888, and we get 95.878. But remember, we have to have the correct number of significant figures. So I'm going to put is equal to, I'm going to estimate here, I'm going to round here. I'm going to put a dot there to show I'm rounding. I need to have one decimal place now. So I need to be here. And I'm going to look over here to see if I'm rounding up or down. And it looks like because there's a 7 there, I'm going to be rounding that up. So I'm going to get 95.9 as my final answer over here to have one decimal place. Otherwise, if I have 3 decimal places here, I'm basically saying that all my measurements are precise enough that you have 3 decimal places, but they're not. You'll notice one of them has 2, one of them has 1. It's really only this measurement here that has 3, and I have to have the same number of decimal places as my least precise one, which is this one over here. And so that's how you would do that if you were doing just addition and just subtraction. Now, sometimes you might have to do multiplication and division. And so for that, it's the same idea. You need to have the fewest number of significant figures. You need to have basically, or I should say it's not the same idea, because in addition, you have to look at the number of decimal places. Now, in multiplication and division, you look at the number of significant figures specifically. And your final answer needs to have the fewest number of significant figures because it needs to match the significant figure of your least precise measurement. So if we look over here, we have 2.6 times 1.35, and we get 3.497. And we have to round to the fewest number of significant figures in our question. So if you look here, we have 2.6, that's 2 significant figures, whereas here we have 3 significant figures for this value here. So we want to round to 2. So we have 3.4, and we look over here, we're rounding that up to 3.5. It's the same idea for division. So let's, for example, do the 900. When you have a slash like this, that means division, divided by 1.345, and we get 669.1449814. And we need to round this to have the same number of significant figures as the one with the fewest number of significant figures in our question. This one over here has 4 significant digits or significant figures. This one over here has 1 significant figure. So I need to round this to have 1 significant figure. So basically I want it over here. I look next door, that's a 6. So this is going to round up to 700. 700, or you could write 7 times 10 to the power of 2 if you remember your scientific notation. But either way, this is 1 significant figure, and this is 1 significant figure, because my value with the fewest number was over here. Now, those were individual calculations. So for example, we just saw, what if you have addition or subtraction and that's it? Or what if you have multiplication or division and that's it? But sometimes you might have a combination of addition, subtraction, multiplication, and division together. And so what do? Well, you follow PEDMAS or BEDMAS, right? Your parentheses, exponents, your division, multiplication, addition, subtraction, order of operations. And then you make sure you follow your addition, multiplication rules as they apply. So if we look at this example here, there's brackets here, parentheses. So we'll do that first, and it's a multiplication. So we get 2.6 times 1.35, and this is 3.51. I'm not going to round right away, but remember, when you're doing a multiplication, what you want to do is you want to make sure you get the same number of sig figs as the one with the fewest sig figs. And so that would be 2. So really, I'm pretending like there's 2 significant figures there, or 2, 2 there, so 3.5 of that. But I'm not going to round it yet. I'm going to keep this in my calculator as 3.51, and I'm going to add the 3.34 now. And so when I do plus 3.34, I get 6.85. But remember, we want to round so that we only have 1 decimal place now, because now my significant figure from here would have been 2. I kept the 1 there just because I don't want to round too often too early, otherwise we're thrown off from our answer. But I remembered that the rule for multiplication is that it's the fewest number of significant figures. So that means it gives me 3.5, which is really just 1 decimal place. And so when I do this addition here, I need 1 decimal place as well. And so I look next door here, and I'm going to round it to 6.9. You might learn that when you have a even number, you actually leave it at the odd. When you have a even number and a 5 after, you leave it at the even number, as opposed to rounding up to the odd. But for now, we're just going to go with regular rounding rules that you may be more familiar with. You can try this one yourself and see if you get the right answer, and then check your work. But right now, you'll notice that I'm adding. So I'm doing 2.45 plus 6.789, and I get 9.239. And I need to remember how many decimal places I want here. The fewest number is 2. So I'm going to just make a little mark here saying that I really have 2 decimal places there. So really a total of 1, 2, 3 significant figures. I'm not going to round right away. I'm leaving the whole number in my calculator, but I'm remembering that I have 3 significant figures there. And now I'm going to multiply it by 3.33. So I have 3 significant figures here, 3 significant figures there. And so overall, it's just going to be 3 significant figures in the end that I need to round to. So times 3.33, and I get 30.7657. And I'm just going to round up here to get my number of sig figs. So it's going to be 30.8. 30.8. That's 3 significant figures. And so that's how you would do it if you have mixed problems. A couple notes to remember. Remember, exact numbers, you count them as infinite number of significant figures. So you're not really going to look at them in your calculation too much. So for example, if I had 20.2 grams of sugar, That's 3 significant digits here. And I want to split it between 2 containers. And so I ask, how much should I put in each container? Well, you would do 20.2 divided by 2, and you get 11.1. And you'd think, well, since there's one significant figure here, I need to make sure I have only one significant figure in my final answer. But remember, this 2 is an exact number, so it really has an infinite number of significant figures. So you don't really count it. You just leave this as having 3 significant figures overall, because this 2 has so many significant figures. Just deal with the 20.2 grams that you have there, because those containers weren't a measurement. They were just an exact number. I have 2 containers here exactly. Likewise, in chemistry, if you have coefficients like 1, 5, 4, 3, coefficients in chemical equations, they're exact numbers. So you're not really going to count them in your significant figure calculations. And then also in your chemistry problems, to make things a little bit easier, when I give you a paragraph or a scenario and there's numbers there, your final answer, just make it have the same number of sig figs as the one that has the fewest sig figs overall. So even if you're mixing problems together and everything, you want to have the fewest number of sig figs as the measurement in the question specifically. So in that little blurb or scenario specifically, that's what you want to have. So fewest number of sig figs as seen in the question.